So here we have a function z, which is a function of two variables x and y, and is given by this polynomial function 4 times x squared times y raised to the power of 4. Then we need to obtain the following partial derivatives. Okay, let us begin. So we'll start with the first one. So we are given here the function z. So z is a function of two variables x comma y. So that is 4 times x squared times y raised to the power of 4. So let's first compute the partial derivative of z with respect to x. So this will be equals to partial with respect to x of 4 times x squared times y raised to the power of 4. Now since we're taking the partial derivative with respect to x, only x will be treated as a variable. Everything else will be treated as a constant. So that means here 4, it's a constant by nature. Y will be treated as a constant. So that means y raised to the power of 4 is also a constant. We can pull it out of the derivative. So we have 4 times y raised to the power of 4. And this will be simply multiplied to partial with respect to x of x squared. Now clearly we're taking the derivative of a function which has only one variable x squared. So what we can do, we can rewrite the partial derivative as a normal derivative, or we can say the ordinary derivative with respect to x of x squared. Now we can use the power rule to obtain the derivative of x squared with respect to x, and that's going to be simply 2x. So we have 4 times y raised to the power of 4 times 2x. Let's simplify this. So we have 4 times 2, that's going to be 8. We have 8 times x times y raised to the power of 4. So this is the value of partial derivative of our function z with respect to x. Now we can also calculate the partial of z with respect to y. So let's do that as well. A partial of z with respect to y. So this time we are taking the derivative with respect to y, meaning so when we take the derivative with respect to y of our function 4 times x squared times y raised to the power of 4, so y will be treated as a variable. Everything else is going to be a constant. That means x squared is a constant. Let's pull 4 times x squared from inside of the derivative. This will get simply multiplied to partial with respect to y of y raised to the power of 4. Or you can say 4x squared times the ordinary derivative of y raised to the power of 4 with respect to y. So that means the derivative of y raised to the power of 4, that's going to be simply 4 times y cubed. That finally we get the value 16x squared y cubed. So this is the partial derivative of our function z with respect to y. Let's go to the third partial derivative. Now this is a second partial derivative. That means second partial derivative of z with respect to x. Now let's try to simplify this. This can be also expressed as partial of z with respect to x. That is what we are going to compute first. And once we have that value, we are again going to take its partial derivative with respect to x. Okay. Now we have already obtained the value of partial of z with respect to x. So partial of z with respect to x came out as 8x times y raised to the power of 4. We have 8xy raised to the power of 4. Fine. So since we are taking the partial derivative with respect to x, so we can treat 8 times y raised to the power of 4 as a constant. Now we are left with the ordinary derivative with respect to x of x. So this is going to be 1. So we have 8y raised to the power of 4. So this is going to be the value of the second partial derivative of our function z with respect to x. Okay, let's calculate the next partial derivative, which is partial derivative of z with respect to y. Okay, we need to compute second partial derivative of z with respect to y. So we can also simplify this as first we will compute the partial derivative of z with respect to y. And once we obtain that particular value, we're again going to take its partial derivative with respect to y. Okay, so this will be equals to partial with respect to y of, so what's the partial derivative of z with respect to y? We've already obtained this value. That's 16x squared times y cubed. And since we're taking the partial derivative with respect to y, so here 16x cubed will be treated as a constant. So 16x squared will be pulled out of the derivative. This will get multiplied to partial with respect to y of y cubed. Or simply we have 16x squared times the ordinary derivative with respect to y of y cubed. So derivative of y cubed with respect to y, that's going to be 3y squared. So we have 16x squared multiplied to 3y squared. So let's find out this value. So 16 times 3, that's going to be 48. So we have 48 times x squared times y squared. Okay, now let's go to the next derivative. So this time we have to take the second partial derivative of z with respect to x followed by with respect to y. Okay, so let's first try to understand this. We have second partial derivative of z with respect to x followed by with respect to y. This means that first what we'll do, we'll take the partial derivative of z with respect to x. So it is always from the right hand side to the left hand side. So that means we take the partial derivative of z with respect to x, and once we obtain that result, we are going to take the partial derivative with respect to y. In the other case, we have second partial derivative of z with respect to y, then we have to take with respect to x. This means that first we take partial of z with respect to y. Whatever answer we obtain, we're going to take its partial derivative with respect to x. Okay, let us begin. So now we have partial with respect to y. So we need partial of z with respect to x. So partial of z with respect to x, we have this value. That's going to be 8xy raised to the power of 4. So we're taking the partial derivative with respect to y. So 8x will be treated as a constant. So this will get multiplied to the ordinary derivative with respect to y of y raised to the power of 4. Right. So we have 8x times, so derivative of y raised to the power of 4, that's 4y cubed. So we have 8 times 4, so that's 32. We have 32xy cubed. Okay, so let's go to the final derivative. So we have partial with respect to x of partial of z with respect to y. We have computed its value, that's 16x squared y cubed. Fine. So this will be equals to, now we are going to treat 16y cube as a constant, and we're going to multiply it to the ordinary derivative with respect to x of simply x squared. We have 16y cube times the derivative of x squared with respect to x, that's simply 2x. So now we have 16 times 2, that's going to be 32 xy cube. Now here we have an interesting result. We see that second partial derivative of z with respect to x followed by with respect to y, this value is equals to second partial derivative of z with respect to y followed by with respect to x. Now this is true because our function which we consider z, the function z is a continuous function. So whenever this particular criterion is met, this is a very important theorem known as the Clairaut's theorem. So we'll come across this theorem later on. So I just wanted to show that this is what the Clairaut's theorem states. Okay, so this is how we can obtain the partial derivative of the function z with respect to the indicated variable.